Hello friends, so today we'll see neighboring group participation and SNi and its another version which is SNi prime, and we will also see some examples regarding these two. For the related videos, that is the previous videos, you will find the links in the description box. So let's start. Neighbor who lives just beside you. So in a similar way, when we are talking about neighboring group, this group, it will be close to the reaction center. Now it participates temporarily in the reaction. It's not, that is a neighboring group, it is not attached to the reaction center permanently. It is temporary. It consists of two SN2 substitution reactions. So first step, that is one SN2, and the second step, that is another SN2. So for SN2 we know it is inversion, and if there are two SN2 going on sequentially, then the net result will be retention. It controls both the rate as well as stereochemistry of the reaction. See how much important it is. And also there is enhanced rate because of this neighboring group participation, and the stereochemistry that we will see in the final product, that is also unexpected. That is not usual stereochemistry that we can normally expect. Now what are the groups that can show neighboring group participation? Here I have given all the examples. Fine. Now see, this is the general mechanism. So for the general mechanism, there are two steps as I have said. So in the step 1, that is step 1, there is attack of internal nucleophile. So internal nucleophile is actually the neighboring group participation. So if you look at this general structure, this is the carbon with which the leaving group is attached, and this is another carbon with which our neighboring group is attached, that is here G. So G is the internal nucleophile. Why? It is attacking this carbon which is carrying this leaving group. So that is why it is internal nucleophile. So this is our first SN2 step. Now in the second step, and here leaving group is already removed. So now we are getting this type of cyclic structure. In the second step, there is another SN2, and here the nucleophile, it is attacking at this carbon. So see, normally if it is simple SN2, what we see, the nucleophile, it always attacks from the opposite side of the leaving group, but here the nucleophile is attacking from the same side, that is the same side where our leaving group is already present. So that is why the final product, we will expect retention of configuration. So in the second step, it is substitution of external nucleophile. So this is our external nucleophile. Okay, so this is the general mechanism. And remember, all these groups, they can show neighboring group participation process. So let's see some examples. Our first example is NGP by pi bonds. So in this molecule, we have a pi bond. OTS. What is OTS? It is tosylate. This is the full structure I have given for your convenience. So this OTS group is actually, it will be removed first. So this is our leaving group. So when it is removed, that when this bond is broken, you are getting a positive charge here. Now this double bond, it will stabilize this carbocation by this type. You can see we are getting two resonance structures. So basically this double bond, it is acting here as NGP. So that is why our heading is NGP by pi bond. So now this carbocation, this positive charge, it spreads over 3 carbon in total. So obviously it will be very stable. So now the external nucleophile that you will use, though that is not written here, it may be any nucleophile, this will attack the carbocation from this side only. Why? Because this side, it is already blocked by this type of bond. So obviously the attack will be from this side. So our net result is retention of configuration. Now see, if you consider the corresponding saturated version of the product, saturated version of the starting material where you do not see any double bond here. So this molecule, the reaction rate, if you do the same reaction under same reaction condition, obviously the first molecule, that is the molecule containing double bond, that will have higher reaction rate. Actually the reaction rate is very high, And why it is so? This is because of the participation of neighboring group, that is the double bond that is present in this molecule. Let's say another example. Our next example is NGP by aromatic ring. So in our starting material, we have an aromatic ring. This is our leaving group. So when it is removed, there will be a positive charge, and the double bond in the aromatic ring, it will stabilize this positive charge. And this positive charge, you can see there are, this positive charge, it is in different conjugated form. It is in resonance. Fine. So our nucleophile, it can attack at this carbon or it can attack at this carbon. Both are possible. So this type of arrow we use for resonance structures. So our final product, though here no question of stereochemistry because it is primary carbon, so it will be CH2CH2Nu. If I draw it, but here neighboring group participation, that is present and that is done by aromatic ring. In the next, we will see NGP by heteroatom lone pair. It may be sulfur, it may be oxygen, it may be nitrogen also. All are heteroatom. So here what is written? Alkaline hydrolysis of Et2N CH2CHCl, then another Et group, it produces Et2N CHET-CH2OH. So what is the structure? So this is our actual structure, that is the molecule starting material that is given. Et2N, then CH2, then CHCl, and then another Et group. Now here this lone pair of electron over nitrogen, it is attacking at this carbon and this CCl bond is broken. So next we will get a cyclic type of structure like that. So here our nucleophile is HO minus. So HO minus, it is attacking at this carbon, because compared to this carbon, the left hand side carbon is sterically better to attack. Okay, so this bond will be broken and finally we will get this product. So our normal expectation is that nucleophile will be attached to this carbon, isn't it? Because this carbon is already containing the leaving group chloride, but actually as NGP is taking place, so finally the nucleophile that is attached to this carbon only, with which Et2 is there. Okay, so the third example, that is NGP by heteroatom lone pair. Next, again we have a problem, and through this problem we will be able to understand more about the NGP process. When R-bromo 2-propanoate ion, it is treated with concentrated sodium hydroxide, then we are getting S2-hydroxypropanoate. So now there is no bromo, there is hydroxy. But if you do the same reaction, but what is the difference? Now you are using low concentration of NaOH or HO minus ion, and also in presence of Ag2O. Now you are getting R2-hydroxypropanoate. So basically when you are using concentrated NaOH, then you are getting inversion, because now we are getting S stereochemistry, not R. But when it is low concentration, you are getting R, that is retention of configuration. So what is the difference that is taking place depending on whether you have taken concentrated NaOH or dilute NaOH? And we will also see what is the role of AgR. So let's look at the first mechanism, that is when you are using concentrated NaOH. So this is a concentrated NaOH. So in concentrated NaOH, we have written the R configuration in this way. And this is the propanoate ion, COO minus. The nucleophile, it is approaching from this side because it is normal SN2. The concentration of HO minus ions are very high. That is the number of HO minus ion in a particular volume, that is very high. So NGP, before the NGP process, SN2 will take place first. So HO minus, that is attacking from the opposite side of Br, and you are getting normal SN2 product with S configuration, and Br is our leaving group. But if it is low concentration of HO minus ion, now what will happen? This CO2 minus, it will act as NGP. So in CO2 minus, it is attacking at this carbon. You are getting this type of cyclic structure. Now this side is blocked, but this side comparatively free. So that is why our nucleophile H2O, it can attack from this side. Instead of H2O, you can also consider HO minus. H2O is written because now you are using low concentration of NaOH. So H2O, actually the products are same whether you are using H2 or HO. So the main point of difference is now we are getting the retention of configuration, because now the HO minus or H2O, our nucleophile, it is not attacking from the left hand side, it is attacking from this side. So we are getting again R configuration, because our incoming nucleophile, it is at the same direction where originally Br is present. Fine. So this is the difference. And here what is the role of Ag2O? Ag2O is actually assisting in the removal of Br minus ion by forming AgBr in the second process. So that is the role of silver oxide. Next we will see how NGP occurs in 1,2-disubstituted cyclohexane system. So here we have taken the cyclohexane system where at 1 and 2 position we have hydroxy group and chloro group. Now cis and trans, both configuration we will see, and it is also important to observe that cis and trans 2-chlorocyclohexanol, they behave differently towards alkali. Now why it is so? So first of all, this structure is general structure. We have not written whether it is cis or trans. But we know that if it is 1,2-disubstituted cyclohexane, if it is cis, then one of the group will be equatorial, another group will be axial. And if it is trans, then both of them should be equatorial or both of them should be axial. Now look at this box. Here, one general structure of trans 1,2-disubstituted cyclohexane system is written. So this is one substituent, this is another substituent. So for NGP to take place, this type of trans-diaxial arrangement, it is very important, because only such conformation, it is suitable for backside attack. So Z, it is attacking this carbon from the backside of X. So X can remove very easily. So that is the reason that NGP process is possible only in trans conformation, not in cis. So that is why they are behaving differently towards alkali. Now first look at the trans conformation, what is happening here. So it is trans, slower reaction involving migration of hydride ion. Sorry, I have done a mistake here. It is not for this. Hydride ion migration, it is not taking place in trans. It is taking place here. Okay. And intramolecular SN2, that is taking place here. So it is just the reverse. Sorry for the mistake. So in the trans configuration, you can see both OH and Cl, both are axial. So O, that is the lone pair of oxygen, it can easily attack this carbon. So it will be now O minus, and the final product, it will be epoxide. So you can find some similarity of this mechanism with this general mechanism that I have written in the right hand side box, isn't it? So this is intramolecular SN2. Why? Because this O minus, it is intramolecular nucleophile. So that is why our final product, this is epoxide. Now when it is cis, the reaction is slower and it involves hydride ion. Now chloro group is axial, but OH group is equatorial. So here OH group is equatorial. So OH group, it is not in a such position just like the previous case that there may be some intramolecular SN2 possible. So as that doesn't happen. So something else happening here. So this hydrogen, it is shifting towards this carbon as hydride shift, and carbon chlorine bond is broken. So finally what we are getting? We are getting cyclohexanone. So from trans our product is epoxide and it is going through intramolecular SN2, that is NGP, but cis there is slower reaction and it involves migration of ion, and our final product is cyclohexanone. So NGP, that is all about NGP when our system is 1,2 disubstituted cyclohexane system. So there is cis conformation possible, trans conformation possible, and both are behaving differently in the reaction. Now how we can prove that NGP is actually taking place? That is the evidence of NGP mechanism. So what we can do? We can do some trapping experiment. So look at the first molecule. There is a OTS group. We have already seen what is OTS group, and this is acetoxy group, OCOCH3. So here acetoxy group, this oxygen, the lone pair over this oxygen, it is acting as a internal nucleophile. It is attacking this carbon, and there is minus OTS. OTS is very good leaving group because the corresponding acetotic acid, that is very acidic. So now we are getting the structure 2 where there is a cyclic trigraph structure and there is a carbocation also. So this existence of acetoxinium ion 2, it has been supported by trapping experiment when the reaction is done in ethanol. Now after this step, if you are using ETOH, then ETO minus, just think about it as H plus and ETO minus, it will attack here, and as a result you are getting the product 4. So this type of structure is actually, it is proving that there must be formation of this type of carbocation, 5-membered cyclic structure. Otherwise how we will get this product, that is the product 4. And there is another possibility, that is 3. There is overall retention of configuration. So this is actually NGP product. This product is NGP product. So here if you are attacking the molecule with acetate ion, then it will attack from the lower side because upper side there is this carbon oxygen bond. So now you are getting the bond which is the not above the plane, it is below the plane. So basically this molecule is 1,2 disubstituted, and in both 1 and 2 position there is OAC group and OAC group. Both are OAC group. So this is our actual NGP retention product because NGP is taking place here. Acetoxy group is behaving as NGP. So it also proves, that is this trapping experiment, it also proves that the reaction is not proceeding by classical SN1 mechanism. Because if it is classical SN1 mechanism, then this fully retention product that we cannot expect. And another possibility, another thing is that here we have trapped this 2 structure, that is a carbocation structure, by using ethanol. So that is why we are getting this molecule 4. Okay, so this is the evidence of NGP mechanism. So that is all about NGP. Now our another part of this video is substitution nucleophilic internal. So substitution nucleophilic internal is for substitution, N for nucleophilic, and internal, I is for internal. So why we are discussing it after NGP? There is some reason. Because here also retention of configuration is taking place, but there is no NGP. So that is why we are discussing it after NGP, so that you will be able to understand that there is no NGP, still how retention is taking place. So that is actually substitution nucleophilic internal. Let's take some example. Our initial molecule is S-alpha phenyl ethanol. Here we are using SOCl2. So again we are getting S-alpha. That means here retention is taking place. So chlorine, that is the incoming nucleophile, that is attached to the same site where OH is already present. That is our leaving group. And these are the side products. Fine. So we'll have to see the mechanism. So first I have drawn the structure, which is that is this molecule, how it is formed. If it is formed by the interaction between OH and SOCl2. So here this hydrogen and one of the chlorine, it will be removed as HCl. So I can write here, that is in the first step you can write HCl. So after the removal of HCl, you are getting this carbon, then O, SO, Cl. Now this carbon oxygen bond, if it is broken, what will happen? You will get intimate ion pair in solvent cage. So that is, as it is present in solvent cage, so that is why this type of third bracket is there. So why it is ion pair? Because there is a positive charge, there is a negative charge. So that is why they are intimate ion pair. They are at these two opposite charge, they are attracting each other. So these two ion, one is positively charged, another one is negatively charged, they will be very close to each other. And as they are very close to each other, stabilized by solvent cage, so what will happen? Now this chloro, it will move towards this C+, and oxygen, this negative charge, it will make a SO double bond. So now you will get SO2 molecule that will be removed because this bond will be broken, and you will get this product with retention of configuration. Fine. So this is the mechanism. Now another point I want to discuss here, that is in presence of pyridine, inversion of configuration is observed. So when you are using pyridine, what is the difference that is taking place? Now you are not getting retention, so must be there is something else is happening. So in presence of pyridine, what happens? Again I have drawn the same structure. See, this is the same structure, just like that. Now instead of formation of this intimate ion pair, the pyridine, it is attacking this sulfur. So Cl will be removed. Okay, already there is one HCl removed, and now this Cl is removed. So what you are getting? Now pyridine is directly attached to sulfur and there is positive charge over nitrogen. So now this side is blocked. And as this side is blocked, chlorine cannot approach this side. That is not possible. So chlorine can attack only through this side. And CO bond will be broken. So when CO bond will be broken, now the new product that you will get, chlorine will be attached to the carbon from the opposite side to which OH is attached. If you look at the initial product, so as chlorine is attached to the left hand side because it is attacking from the left hand side, so this is our structure. So in presence of pyridine, now we are getting inversion of configuration. Now there is no such intimate ion pair. Fine. So now this is not SNi. SNi is the first mechanism, that is I have shown here. In presence of pyridine, something else is taking place. So this is all about SNi. Next, see what is SNi prime. So when the in SN1 prime and SN2 prime, we have already seen in previous videos that mostly when you change the substrate to allylic version, then the prime reactions occur. That is, if it is SN1 prime, SN2 prime, and also here the same case, that is SNi prime also, your substrate is now allylic one. So nucleophilic attack, it will occur at the gamma carbon. So in this molecule you can see I have marked all the carbons here, gamma, beta, alpha. So with alpha carbon, leaving group is attached, but the final product that you are getting, that is the incoming nucleophile, that is attached to the gamma carbon. So attack occurs at gamma carbon rather than alpha carbon. So this type of mechanism is SNi prime mechanism. So again I have written the structure which is the product of after the first step, because OH, there will be interaction between OH and SOCl2, and this type of structure you will get. This type of structure you have already seen in the previous slide. Just remember this one, that is the blue structure. So first OSOCl it is formed, and after that if you draw the same structure, there is a equivalent sign I have given. So if you draw the same structure in a different way, so that it will be easier for us to understand the mechanism. Now the alpha carbon and oxygen, then this bond will be broken. So there will be a positive charge and there will be negative charge over oxygen, and this chloro and sulfur bond will be broken, and the lone pair over chlorine, it is attacking here. So this is actually our gamma carbon. This is beta, this is alpha. So this is our final product. So if you look carefully, in the problem, the product that is written, this is actually same. These two are same, isn't it? So here attack is taking place at gamma carbon, not at alpha carbon. So that is SNi prime mechanism. I hope you will find the video helpful, and if it is the case, then please like, subscribe and share my channel. Thank you for your attention.